Okay, this is a lecture on chapter 4 of conceptual physics, it's about Newton's second law of motion. So let's get started here. Force causes acceleration. We'll see that if you apply a force, if the net force, uh, if there is a net force, you will accelerate a mass. We'll learn about friction. Friction will reduce uh, the the more friction there is, the more it'll reduce the net force on an object. We'll learn the comparison between mass and weight. Mass is an inherent property of a material. Weight is dependent on where you're located. A mass on the moon is different than a mass on the Earth because of the gravitational acceleration of the moon is different than the gravitational acceleration on the Earth. And we'll learn about the Newton's second law of motion. Force equals mass times acceleration. That's what it's going to come down to. Just a little preview. We'll talk about free fall and non-free fall. So let's get started. Acceleration is directly proportional to net force. To increase the acceleration of an object, you increase the net force acting on it. So acceleration is related to net force. Okay, the force of friction. Now, if I were to have two blocks of wood, smooth blocks of wood, I could slide those together pretty easily. Now, if I take sandpaper to one side and sandpaper to the opposite side of to the opposite block, but with the sides facing each other, I would have a harder time sliding those blocks together. Why? I've increased the little tiny surface bumps. Look at this. Let's look at these bullet points. It depends on the kinds of material and how much they're pressed together. It's due to this tiny surface bumps and to the stickiness of the atoms in a material surface. There's not, if you take some like saran wrap on a and you stick it to a glass bowl, that's that's more the stickiness from the atomic structure, the atoms in the saran wrap and the glass bowl. There's no bumps in it. The glass is smooth and the saran wrap is pretty smooth. Okay. They give an example. The friction between the crate on a smooth wooden floor is less than on a rough floor. Again, think of those blocks of wood with sandpaper. With no sandpaper, they slide pretty easily. With sandpaper, they're going to stick. You'll have a hard time. Okay, the force of friction can occur with sliding objects, in water, in air, all of the above. Well, the truth is all of the above. I mean, if you were to be in a boat and you have your motor on and you stop the motor, the boat's not going to keep going because of inertia. It's going to slow down because of the friction between the boat and the surface of the water. So all of the above. Friction can also occur for objects at rest. If you push horizontally on your book and it doesn't move, then friction between the book and the table is opposing your push. Okay, when Sanjay pushes a refrigerator across the kitchen floor at a constant speed, the force of friction between the refrigerator and the floor is A, less than Sanjay's push, B, equal to Sanjay's push, C, equal and opposite to Sanjay's push, or D, more than Sanjay's push. Well, the key point here is constant speed. If it's a constant speed, then we know that the sum of the forces equals 0. So he's pushing in one way. Friction has to be in the opposite direction, but equal, and that's C. C. It's equal and opposite to Sanjay's push. Okay. When Sanjay pushes a refrigerator across the kitchen floor at an increasing speed, the force of friction between the refrigerator and the floor is now increasing speed. That means Sanjay, the net force is, if it's increasing, it's in the direction that Sanjay is pushing. So the force of friction is less than Sanjay's push, is equal to Sanjay's push, is equal and opposite to Sanjay's push or more than Sanjay's push? Well, it's A, it's less than. Um, the increasing speed indicates a net force greater than zero. The refrigerator is not in dynamic equilibrium. Okay, let's go to mass and weight. Um, the quantity of matter, mass is the quantity of matter in an object. It also the measure of the inertia or sluggishness that an object exhibits in response to an effort made to start it, stop it, or change its state of motion in any way. Um, and weight is usually a force upon an object due to gravity. So when the astronauts were training to have these big life support backpacks, you know, the backpacks were, I think they were, you know, hundreds of I don't know if it was pounds or kilograms. So on the moon they were able to carry them because the gravitational force on the moon is a whole lot less than it is on the Earth. So they gave the astronauts a smaller weight on the Earth to train with, and you know, so it simulated the mass, it simulated the weight that the backpack would have on the Earth, and so they could get used to it. What they didn't account for is the inertia. Yes, it simulated the uh, uh, the weight of the weight that what they would experience with the backpack on the Earth, but to move with that large backpack on your back, there was a lot more inertia, and they had to get used to swinging that backpack around. The they had already trained on the weight, the simulated weight here on Earth, but they did not account for the inertia. So they got used to it, but it was an interesting difference. The inertia that much mass had was different than what they trained for on the Earth. Um, okay, mass is a measure of the inertia of a material or object. It's independent of gravity. The greater inertia, the greater the mass. The unit of measurement is the kilogram. Um, weight is usually the force of an object due to gravity. Standard unit of force is the Newton. Another common unit is the pound. Pound is not mass. Pound is related to the gravitational force. So if you weigh 200 pounds on the Earth, you'll weigh 1/6 of that on the moon. Okay, if the mass of an object is halved, the weight of the object is halved, right? It's halved. It's not twice. It does depend on the location, but it is halved. Weight and mass are directly proportional to each other. So, okay, mass and weight in everyday conversation are used interchangeably, but they're not really. In the physics concept, mass and weight are distinct concepts. However, mass is more fundamental than weight. Mass versus weight on the moon and Earth. The weight of an object on the moon is less than on the Earth. The mass of an object is the same in both locations. So the mass is going to be the same. You take a 1 kilogram mass here on the Earth, it's going to be a 1 kilogram mass on the moon, but it'll be it won't have as much force. The force of gravity is less on the moon. Okay, 1 kilogram weighs 9.8 newtons on Earth's surface. The relationship between kilograms and pounds. 1 kilogram weighs about 2.2 pounds at Earth's surface. 1 pound equals 4.45 newtons. When our kids, my wife is from Mexico, so whenever, my wife has been here in the United States since she was 2, but my mother-in-law, more than my father-in-law, my mother-in-law did not do conversions well. So when ever we had a kid born, she would want we had 4 kids. She would want she would want to hear their weight. It wasn't their weight, their mass. She would want to hear the mass in kilograms, not pounds. But I always have to do the conversion for her. Okay. When the string is pulled down, we have a string. I hope my image isn't interfering, but you have a string supported from a little block or something that's holding this weight, and then you're pulling on the bottom of the weight with the string. When the string is pulled down slowly, the top spring breaks, which best illustrates A, the weight of the ball, B, the mass of the ball, C, the volume of the ball, or D, the density of the ball. And I may be wrong, but I'm going to say it's A, the weight of the ball. And it is. When the string is pulled down slowly, the string breaks, which best illustrates the weight of the ball, because the tension in the top string is the pulling tension in the bottom, what you're pulling on the bottom, plus the weight of the ball. So the top string has greater tension and breaks first. So when you're pulling the bottom, all it is the tension that you're applying, but the top string has both that tension and the weight of the ball. Now, when the string is pulled down quickly, when you pull it down quickly, the bottom string breaks, which best illustrates the weight of the ball, the mass of the ball, the volume of the ball, or the density of the ball. Well, it's B. It's inertia. In other words, when you pull quickly, the inertia of the ball, its tendency is to stay at rest. So when you pull the string, the bottom string breaks. Let's see if I got that right. The laziness of the ball, that's another way of saying the inertia of the ball, tends to keep it at rest. If the bottom string is pulled faster than the response time needed for the ball to move slightly, the tension in the bottom string will exceed the tension in the top string. Okay, let's see. Mass resists acceleration. The same force applied to twice the mass produces half the acceleration. 3 times the mass produces 1/3 the acceleration. So acceleration is proportional to the inverse of the mass. In other words, if this increases, what's greater, 1/2 or 1/4? It's 1/2 is greater. So in other words, as this goes up, this goes down. The acceleration decreases as the mass increases. Acceleration is inversely proportional to the mass. Okay. Isaac Newton was the first to connect the concepts of force and mass to produce acceleration. And here is his Newton's second law. And the acceleration, let's think of it in 3 parts. The acceleration produced by a net force on an object is directly proportional to the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. Now, let's look at the second one, is in the same direction as the net force. Let's see, does he get well, we'll get there. Force equals mass times acceleration, or the way he has it here, acceleration is equal to the net force divided by the mass. Acceleration is a vector. The net force is a vector. If you multiply or divide a vector by a scalar, mass is a scalar, you're going to get the same direction of the vector, only in different proportion. So the fact that if we go back here, it's in the same direction as the net force, it's because the acceleration and the net force are vectors, whereas the mass is just a scalar. A scalar will not change the direction of a vector. It just makes it bigger or smaller. So since it's dividing, if the mass increases, the acceleration decreases. Examples: if the net force acting on an object is doubled, then the object's acceleration will be doubled. It's in the numerator. So if you increase this, the acceleration will increase. If the mass of the object is doubled, then the object's acceleration will be halved. So if you apply a net force and you have a mass of 2 kilograms, you'll get a certain acceleration. If you take that same net force and now you have 4 kilograms, you've doubled the mass, so you've cut your acceleration in half. Okay. Here's some examples. The force of a hand accelerates the brick twice as much force. He's pushing with 2 hands. Is twice as much acceleration. Twice the force on twice the mass gives the same acceleration. This one here gives the same acceleration as this. Now let's look at this column. The force of the hand accelerates the brick, same as here. The same force accelerates 2 bricks 1/2 as much. Okay, he's still only pushing with 1 hand. 3 bricks, it's 1/3 as much as the acceleration. Okay, let's see. Consider a cart pushed along a track with a certain force. If the force remains the same while the mass of the cart decreases to half, the acceleration of the cart, let's see, if the force remains the same while the mass of the cart decreases to a half, the acceleration of the cart it remains relatively the same, it halves, it doubles, or it changes unpredictably. Well, remember, it's in the denominator. The mass is in the denominator. So if the mass decreases, the acceleration has to increase. So it decreases by half, it has to double. It doubles. Remember, the mass is in the denominator. So if it goes down, acceleration has to come up. If the mass goes up, the acceleration has to come down. Because mass is in the denominator, acceleration increases as mass decreases. So if mass is half, acceleration doubles. Okay, the net force on the cart on a level track is doubled. If the acceleration does not change, what is a possible explanation? The mass of the cart doubled when the force doubled. The mass of the cart halved when the force doubled. Newton's laws become modified, but we know that's not going to happen. Newton's laws are they can't be modified. And friction reverse direction. Well, the only logical explanation is A, the mass of the cart doubled when the force doubled. If net force doubles while mass remains constant, the acceleration would double. Doubling the net force and doubling the mass results in no change in acceleration. Okay, free fall. We covered this a little bit in the I guess it was in chapter 2. I even presented a video of a feather and in one video, it's a feather and a bowling ball in a NASA vacuum chamber. And in other words, it's the astronaut dropping a hammer and a feather on the surface of the moon. I'll provide links to those again in case you didn't see it in chapter 2. The greater the mass of an object, the greater its force of attraction towards the Earth. That is, the greater its weight. The smaller its tendency to move, that is the greater its inertia. The more you double it, it has greater inertia. It doesn't want to be moved. Or if it's moving, it wants to stay moving more than one that's half of the mass. So acceleration of both sets of the bricks is the same. It's gravitational acceleration. Twice the force on twice the mass gives the same acceleration, g. The acceleration of both sets of bricks is the same, approximately 10 meters per second squared. To be exact, 9.8 meters per second squared. So here you can see one mass, and the force divided by the mass is equal to g. Here, twice the force divided by twice the mass is equal to the same g. Okay? Okay, at one instant, an object in free fall has a downward speed of 40 meters per second. The speed 1 second late, its speed 1 second later is, well, we're using a gravitational acceleration of 10 meters per second squared. In other words, every second, it's going to increase by 10 meters per second. So if it's 40 meters per second, 1 second later in free fall, it's going to be what? It's going to be 50 meters per second. If the object was upward with no force on it, but gravity, it would nevertheless be in free fall. In that case, after 1 second, its speed would decrease from 40 meters per second to 30 meters per second. In other words, you have 40 meters per second, but the gravitational acceleration is downward, so it's going to decrease it by 10, and it'll be 30 meters per second. Okay, a 5 kilogram iron ball and a 10 kilogram iron ball are dropped from rest. For negligible air resistance, the acceleration of the heavy ball will be, now it says for negligible air resistance, will be less, the same, more, or undetermined. And it's going to be the same. That was Galileo's. It's probably an apocryphal story. It didn't really happen, but it makes a nice demonstration. Supposedly Galileo dropped two different masses of cannonballs from the Tower of Pisa, and lo and behold, they reached the bottom at the same time. So it'll be the same. Okay, a 5 kilogram iron ball and a 10 kilogram iron ball are dropped from rest. When the free falling 5 kilogram ball reaches a speed of 10 meters per second, the speed of the free falling 10 kilogram ball is, if we go back here, the same. So if the 5 kilogram ball reaches 10 meters per second, then B, 10 meters per second. No, both are in free fall, hence they're equal speeds. Okay. When an object falls downward through air, it experiences a force of gravity pulling it downward, and air drag force acting upward. When you first drop an object out of the sky, like a skydiver jumping out of a plane in the sky, he's going to increase his speed until he reaches what is called terminal velocity, where his downward gravitational force is equal to his resistance force. Now, part of the resistance is your surface area. So you can see the skydivers, they're spread eagle. They've got their arms and their legs spread out, and they've reached a certain terminal velocity. What happens if he were to cut his cross-sectional area by moving his arms and his legs together, and even pointing his head downward to where he presents a very narrow, very small cross area to his fall? He's going to increase in speed. Because he's presenting a smaller cross-sectional area to the air resistance. Okay. The condition of non-free fall occurs when air resistance is non-negligible. And it depends on two things. It depends on speed and the frontal surface area. That's what I was talking about, the skydiver. The more he's spread eagle, spread out with his arms and legs, he's presenting more frontal surface area. If he tucks those in and heads straight downward, head first, he's presenting a smaller frontal surface area. Okay, when the object is moving fast enough, so that the air resistance builds up to balance the force of gravity, then there's no net force. The downward gravitational force equals the resistance force, the big R here in the image. There's no acceleration. Velocity does not change. It reaches terminal velocity. Okay, terminal speed occurs when acceleration terminates, when air resistance balances weight so that the net force is zero. Terminal velocity refers to terminal speed along with the direction of motion, which is downward. Okay. Let's see. Non-free fall example: a skydiver in fall after jumping from a plane. Weight and air resistance act on the falling object. As falling speed increases, air resistance on the diver builds up, the net force is reduced, and the acceleration is reduced. If the net force is reduced, the acceleration is reduced. Because remember, it's the force and acceleration are proportional, directly proportional. Mass is inversely proportional. When air resistance equals the diver's weight, net force is zero and acceleration terminates. The diver reaches terminal velocity, then continues to fall at constant speed. When a 20 Newton falling object encounters 5 newtons of air resistance, its acceleration of fall is less than g, more than g, or terminated. Well, 20 newtons minus 5 newtons of air resistance is going to give you 15 newtons, which is for the mass. It's probably a 2 kilogram object if it's a 20 Newton object. So it's less than g. Acceleration of a non-free fall object is always less than g. Acceleration will actually be, you take the 20 divided by the, not divided, the 20 minus the 5 gives you 15, divided by 2 gives you 7.5 meters per second square. Just got a notification that the Cowboys won. Okay, that's what the beep was. Okay, if a 50 Newton person falls at terminal speed, the air resistance is less than 50 newtons, 50 newtons, more than 50 newtons, or none of the above. The key point here is terminal speed means that he's not accelerating any longer. He's reached his final speed. If that's the case, then the sum of the forces equals 0. And if he's 50 newtons, then the air resistance has to be 50 newtons, exactly 50 newtons, and that's B. Terminal speed means acceleration is 0, which implies that the net force is 0. Thus, the upward air resistance force has the same magnitude as the person's weight. Okay. As the skydiver falls faster and faster through the air resistance increases, decreases, remains the same, or there's not enough information. Well, it increases. It's related to speed, cross-sectional area. It's related to a lot of things. But if he's increasing, then the air resistance is increasing until it increases so much that it equals his weight. That's when he reaches terminal velocity, or she. As the skydiver continues to fall faster and faster through the air, net force increases, decreases, remains the same, or not enough information. Well, as her velocity increases, the net force, it has to decrease because it's headed towards 0 where she reaches terminal velocity. So it decreases. Okay, as the skydiver continues to fall faster and faster through the air, her acceleration increases, decreases, remains the same, or not enough information. Well, if the net force is decreasing, her acceleration has to be decreasing because acceleration is directly proportional to the net force. So her acceleration decreases. Okay, consider a heavy and a light person jumping together with the same size parachute from the same altitude. Who will reach the ground first? The light person, the heavy person, both will reach at the same time. Not enough information is provided. Well, it's going to be the heavy person because both people feel a similar upward drag force at any given speed. The heavier person has a greater downward weight force than the lighter person. Thus, the heavier person must drop further before the upward drag force balances the downward weight force, resulting in a greater terminal speed. Okay, a rock and a feather. Now, you've seen this demonstration, and I'll include it again in the canvas. A rock and a feather fall while air is present. The feather reaches terminal velocity quickly, then falls slowly at a constant speed. The rock's fall takes more time for air resistance to balance its weight. Owing to its greater terminal speed, it reaches the bottom before the feather. Okay. If the rock and feather are dropped in a space where the air has been removed by a vacuum pump, we've seen this demonstration. The feather hits the bottom first before the rock hits. The rock hits the bottom first before the feather hits. The rock and feather drop together side by side, or D, more information is needed. You've seen the video, or you should have seen the video. If not, look up on YouTube rock and feather in a vacuum chamber or something similar to that, and you'll see it. The rock and feather drop together side by side. Okay, coin and a feather fall in vacuum. There is no air because it is a vacuum, so no air resistance. The coin and the feather fall together. Okay, and that's the end of the PowerPoint. I'll provide you with some homework examples and some homework problems in the next day or two.